Hello, hello everybody. Welcome to the lecture of the downstream processing in biotechnology. This lecture will continue on the adsorption. As like previously, we talked about the adsorption operation, like in batch operation, in continuous stirred tank operation. But now we will concentrate on the adsorption in a fixed bed. Fixed bed adsorption is the most common use for the adsorption process to separate liquid or gas solute from the mixture. Mixture. The fixed base mean the adsorbent is fixed, and solution of fluid flow to the bed. That's right. The commercial adsorption operation are performed like unsteady state process. What does it mean? Unsteady state process. Liquid containing the solute flow past to the bed, and the loading or amount of the product retained in the column will increase with time. That's right. This is the unsteady state operation. That means amount of adsorbent accumulate in the surface or on the surface of the solid adsorbent will increase with time. But this case, only the fluid or solution is flow, is moving. That's right. Mostly it's flow from the top to bottom. That's right. And the adsorbent is fixed in the column or fixed in the tube, something like that. We call the fixed bed adsorbent. Right? It show you the example of the fixed bed. And we have the tube. Inside the tube we packed with adsorbent, that's why we pack it adsorbent, and also this is the fluid flow from the top to the bottom, like from the top to bottom. And the graph show the different concentration or the concentration at the output of the column vary with time. That's right. The solid, right? Solid symbol, like a black symbol, like this is the area or the solid that saturated or in equilibrium with the solute. A chat area is an area that can adsorption. It's like adsorption show. That means the adsorbent and adsorbate. Adsorbate is adsorb or accumulate to the surface. And the circle, right, with no solid. That's like a circle with a solid. Right, is the dark solid is a chat solid is the empty solid symbol. Empty solid symbol it means only the adsorbent. There is no adsorbate accumulate on the surface. That's right, adsorbate accumulate. Okay, if we consider at T1 at the start, we feed the solid or the liquid with the concentration of CAI. CAI is the concentration of solute in the feed. That's right. Okay, at this time, when the solution contact with the saturated zone or contact with the adsorbent, then mean adsorption occur. That's right. Solute accumulate to the adsorbent. Yes, to the adsorbent, and then the fluid flow to and out to be CA1. CA1 mostly it approach zero. Why approach zero? Because most amount of solute is absorbed. It's absorbed in the surface of the on the surface of the adsorbent. That means very slow amount. That's right, very slow amount of solute. That's right, flow out. That's been okay. For CA1 at T1, the concentration is approach zero, and then the feed continue flow to the pack of the adsorbent. At this zone, that's right, at this zone, the adsorbent is saturated with adsorbate already. That means for T2, that's right, T2. For T2, and this zone is saturated already. And then the adsorption zone is moved downward. That's right, this is the adsorption zone. This is saturated zone. That's right, this is the unabsorbed zone. That's the unused adsorbent. Okay, for this case, the feed continue flow. The saturation is increased. That's right. The level of the saturation zone is increased. The unused is decreased. That's right. The high of the unused is decreased. The saturation is increased. That's right. And also, this is CA2 is also approach to zero. It's approach to zero because the adsorbent still work. As I still work, they are an empty solvent. They are an adsorption zone. This is the saturation zone. And then if we flow is continually until T3, the saturated zone is increased. That's right. The saturated zone means the adsorbent, that's right, have an absorbate attached to the surface already. Okay. There are some little zone on the adsorption. That's right. It is saturated already, this zone. And this is the adsorption. That's right. If we flow this continually, that's right, and continually, some amount of solute will absorb by this adsorbent, right? If the in full with the adsorbate or saturated with adsorbate, if you feed further, yes, if you feed further, the solute cannot absorb to the surface of the adsorbent because there is no the site. There is no the site for the solute. That means if you feed further, the concentration of solute increase rapidly until it's T4. That's right, at time T4. CA4 is approximately the same CAI. What does it mean after this time? When you feed CAI, CA out and CAI is the same because the adsorbent is saturated with solute already. There is no the site for the adsorbent. There is no site for the adsorbent. Okay, this is the phenomena of the adsorption with the packed column or fixed bed. That's right, or fixed bed. What is the next? Because it is you use all of the adsorbent already. If you feed the liquid further, there is no adsorption. The next step you have to regenerate. Right? Later you regenerate. Before regenerate, you have to dissolve the solute by some solvent to dissolve the solute. This is the circle. That's why with the cycle. You have the adsorption. Sometimes you have to watch some unabsorption, and then you have to dissolve by solvent and washing, or what the diluent or solvent, and then regenerate. After you generate, you can use the adsorbent again. That's right. It shows some between T3 and T4. For this case, when you increase flow of the feed, concentration at the outlet increase rapidly until the concentration in the feed. That's mean. For this area, we call it the solute loss in. Why we call it solute loss? Because when you feed the solution, solute will not be adsorbed. That's right, flow in, and some solute is flow out, not dissolved. We call it the loss of solute. That's right. Okay, and for this case, we can separate half and a half. That's right. Because this solute loss in the flow end, and this is the unused bed capacity. Unused bed capacity. That means we will stop. That's right. We will stop the adsorption before it's lit T4. If lit T4, if you feed CA, the outlet is also the same CI. This is no adsorption. Okay, we can stop before T4 is allowed half. In this case, you can save right solute, and there is some unused adsorbent for this case. This is the unused adsorbent. This is lot of solute, something like this, This is the phenomena of the adsorption in the figure of Hackman. Okay. If we draw the concentration at a high of the column, this is the high from 0 at the top to the bottom. At the top to the bottom, you can see that the equilibrium zone will increase from the top to the bottom. But we will stop around here. That's around here. There are some adsorption, but we only absorb some in this time, and this is the lot of solute, thing like this. Okay, if we consider the fixed bed, in the column, we fix packed with solid adsorbent. Okay, liquid flow in at the top. For out, if we consider a small volume, what happens in the small volume like this? Liquid flow in, liquid flow out. And also there is some exhale diffusion like this. We feed with flow rate F, concentration is CF, and the concentration C is outlet, and F is the flow rate. We assume flow of liquid is constant. the size is constant. If it dilute, okay, we can assume constant. If we consider the mass balance, if we consider a mass flow into the boundary, flow in like this, flow out, flow in and flow out. Mass generation in the system. The system is a small volume like this. Mass consumption or mass consumed. For in this case, there is no mass consumption or mass consumed. That's why we have no reaction. If there is no reaction, right? And this mass accumulate in the system. Okay. For this case, we can mass balance, and then finally you get the equation. For this case, quite complex equation is the partial differential equation. Okay. After you make the mass balance or the solute in liquid, we have 1, 2, 3, 4 term. In this term is the axial dispersion. This is the flow. That's flow, and this is the flow. Flow from the top to the bottom is the dispersion. Back diffusion. This is the diffusion. And this is the concentration change or accumulation of the solute in the white. Because we have the solid and we have the white of the plate that solute or liquid or fluid can flow. That's right. The white is also the white the place between solid and also inside the pore. Okay, and this is 1 minus epsilon dq by dt. This is the concentration of solute accumulate in adsorbent or accumulate by adsorption. As I did accumulate by adsorption. This is the amount of solute accumulation in the interstice or in the void. That's right, or in the void. For this case, we have 3 terms, right? We got the diffusion, axial diffusion, have the flow in and flow out, accumulation in the void, and accumulation in the adsorbent or adsorption. And also we define the void is the total volume of the column minus the volume of solid divided by the total volume of the tank. This is the void fraction. That's the void fraction. And also mostly we can cancel like dAz. dAz means diffusivity in axial dispersion. That's like in axial dispersion. And also we can cancel, but mostly dAz or axial dispersion is greater than molecular diffusion. Molecular diffusion is diffusion between molecules. That's right. Is greater than molecular diffusion. Okay, for this can we incorporate the acid, that's right, in the adsorption analysis also. Okay, and U is velocity. U is the interstitial velocity of liquid. That means the velocity of liquid in the water. Liquid in the water. That means it's equal to flow rate or volumetric flow rate divided by the cross-sectional area of the column multiplied by void fraction. That's right. Multiplied by void fraction. Because it is the flow in the void fraction, not flow in the column. Okay. Or the assumption to simplify the equation like this, because it's quite difficult. This is the partial differential equation because we have 2 different equations and 2 independent equations. C and Q is dependent equation. Z and T is independent equation. This is the partial differential equation. Quite complex. That's okay. For assumption, for this case, you have to reduce or cancel the axial dispersion. Axial dispersion is quite small when you compare to the flow in, flow out. And also we compare to the solute adsorb on the liquid. Okay, we can cancel the axial dispersion. And also the interstitial fluid content in the bed is small when compared to the total volume. That means the void fraction is quite small compared to the solid. Okay, we can cancel term of the accumulation in the void and term of the axial dispersion. Okay, finally you get only 2 terms. That's right. Accumulation or the flow in, flow out, and accumulation in the solid or in the adsorbent is the main effect. Okay, did it show you right the phenomena? We have solid, and inside of we have the pore. We know that when we flow of solid in the liquid or in the fluid, there are some film. This is the gas film is fluid is gas, or liquid film is fluid is liquid. Okay, for this case, it's liquid film. that's a liquid film, or the liquid will transfer from the bulk to the surface or interface between film and liquid. That's right. And the next step we diffuse through the film. That's right. Mostly in the film there is no convection. The convection is very small effect. But the main effect is the diffusion. And also if so you diffuse in the film and then until with the surface of the solid. That's right. And number 3 is the diffusion inside the pore. That's right. The diffusion of the solute inside the pore. Number 4 is adsorption. That's right. The solid accumulate on the surface. That's right. Accumulate on the surface. And number five is the incorporation or the change or movement in the surface of the solute in the adsorbent surface inside the pore. That is the mechanism of the diffusion. Of the diffusion. Okay. Mostly, that's right. The mass balance of solute in the sorbent. Previously, we talked about the mass balance in the solution. But now, if we talk about the mass balance of solute in the solvent, that means accumulation of the solute on the solvent equal to rate of adsorption. That's right. This is the accumulation of the solute on the solvent surface equal to rate of adsorption. That's right, rate of absorption. If the adsorption rate is linear, we can express I equal to KAC minus C star. K is mass transfer coefficient. A is the surface area per unit volume of solid. C is concentration in liquid phase. Theta is equilibrium concentration in liquid phase at the exit of the column. That's right, at the exit of the column. Okay. For this case, that we have to write the mass balance of solute in solvent at mass balance of solute in the liquid phase. This equation. This equation together with the rate of adsorption. Okay. For this case, it's also two equations. That's right, and are quite complex. We can not solve easily. We have at least 4 models. I will talk to you. Right? The first model is an approximate analysis. The second, we have 2 model parameters. And the third, if we show it the linear adsorption model, or we assume like the isotherm is linear, something like this. And also the last one, like differential contacting method or model. The first one, if we use an approximate analysis. For approximate analysis, we consider like the curve as we showed previously. We talked about the breakthrough curve. We call this is the breakthrough curve. That's right. In this case, we consider this scheme. That's right. Mostly, we will operate at C breakthrough. Breakthrough means the point after you increase or after you feed faster, the concentration in the output will increase rapidly. At that point, it's about 5% of CF. That's not 5% of CF. That means the concentration is 5% of CF. That's right. And also, we call this TB, T as break point, and TE, the X has point. X has point means all of the solute that you feed equal the solute that output. That's right. For this case, we can calculate the TE at approximately 95% CF. That's right. For breakthrough, we calculate about 5% CF. For E, it's about 95% CF. Okay. This case, we back to the discovery. So we have the adsorption zone and equilibrium zone. At equilibrium zone, we talk this about TB. Okay. For the equilibrium zone, from Z to 0 until Z to L multiplied by 1 minus delta T divided by TB. Delta T is the GX class divided minus TB. And the adsorption zone, the length of the adsorption zone is the adsorption zone. Right. This is the delta T divided by TB. And then you can calculate or approximate the equilibrium zone constant is about half load adsorbent at the half load adsorbent. Okay, and then you can calculate the fraction of bed that is low. Like this equation. Equal to 1 minus delta T divided by 2 TB is a half. That's a half of the delta T divided by TB. That means shorter the adsorption zone, the more complete the bed is low. That's right, is low. If we shorter the adsorption zone, that means we can use effectively adsorption, because adsorption equilibrium or equilibrium zone, that means we can adsorption zone that you still adsorb, and also we may unused adsorbent. Right? Okay, this is the first model. Like it. The second model, we talk about the two-parameter model. We can use the two-parameter model. For this case, we fit the breakthrough curve like this curve, like this curve with some equation. For this case, we fit with this equation is the ratio of C divided by CF. C is the concentration at the output, or effluent concentration. CF is the feed concentration, is a function of time, and sigma in terms of early function. T0 is the time as with the exit concentration is half of the feed concentration. T0 is the exit concentration is half of the feed concentration is C equal to 0.5 C. That's right. Sigma T0 represents the standard deviation. That is the slope of the curve. Okay, this is depend. The deviation is depend on the velocity and the length of the column. Right? For equilibrium, if you control equilibrium, that's divided by L. 1 divided by L. That's the variance is L divided by U square. Or kinetic of adsorption is the main effect. That's right. U divided by L for the sigma square. And variance is L over U. Okay. The mass transfer is the main. This is a square root of U divided by L. This is the L divided by U square root T. That's right. Square root over 3. That's right. And dispersion and diffusion. We can use this to consider what is the main effect or the controlling step. Right. And the third one, like linear adsorption model. For linear adsorption model, for this case, we assume the isotherm or equilibrium relationship is Q equal to Kc. Is linear relationship. That's like concentration at equilibrium of solute in adsorbent equal to K multiplied by concentration of solute in the liquid phase at equilibrium. For this case, we assume further that the dispersion model dAz is negative. That's right, it's negative because it's very small relative to the total volume of fluid. The mass balance, okay, we can reduce the mass balance. Right? So the mass balance, you can equation like this: minus U dC by dz minus Kc minus Q over K. It is rate of adsorption. That's right, the rate of adsorption equal to Kc minus C theta. C theta is Q over K. That's right. And for this term, so we have two, that is solute balance in the liquid phase. This is solute balance in the liquid phase. This is the solute balance in the adsorbent. 1 minus epsilon dq by dt equal to KAC minus Q over K. That's right. For this equation, we use the condition like at T0 or the length or the height of the Q equal to 0. That means at the start, there is no solute in the adsorbent surface. At T greater than 0, at the inlet at 0, C equal to C feet. This is the condition to solve for these two equations. That's right. For these two equations, we use this condition. So, okay. After you solve by analytical, and then solving solution in terms of this graph. This graph shows the relationship between J and T. J is the ratio of C over CF. Effluent concentration divided by feed concentration. T is the KAT minus Z over U K1 minus T. That's the T. And also, it's very with like S equal to 0.1, something S equal to Z KA over U. For this solution, we explain in terms of graph. That's right, for T parameter. You can estimate, like you can estimate Ka, you can estimate C. If you know T, you know J, you can calculate S. That's right. If you know S, you know T, you can calculate C like this. You can use this equation. And the last model, we call it the differential contacting model. Differential contacting model. For this case, we consider the mass balance around the column. That's right. For this case, we assume by the flow of the liquid phase and flow of the solute that in the adsorbent is counter current to the solution. If the bed is infinitely long, that's why we assume if the bed is very long or with very high, it can accomplish separation at steady state. That's right. The concentration at the entrance of this bed are in equilibrium. CF equilibrium with Q. That's right. Is it in equilibrium? Is it in equilibrium? That's right. For this case, is for a long, or the very high column. The concentration at the exit we assume is 0. That's right. And the concentration in the adsorbent at the start is 0 for this case. And then you make a mass balance. That's right. With the steady state mass balance. Input equal to output. No reaction, no generation, no consumption. That's right. That means HC equal to WQ. That's right. It's in. That's right. C equal to Q WQ. So this is we call this the operating line. We call this operating line. That's like HCCF. That's like for this CF minus 0. That's like equal to WQ minus 0 for this case. Okay, we call this operating line. If you plot this curve and also with the equilibrium line show like that. So equilibrium line is maybe okay. This equation Q equal to KC star, and another equation is HC equal to WQ. That's right. Mostly for this case, maybe the equilibrium line is not linear. That's right. It's not linear. It's maybe linear or not linear. For this case, you can assume it's linear or not linear. It depends on the real, in the real data. Okay. For this case, you can plot like this. This is the operating line. Previous the operating line is linear relationship, and this is the equilibrium line. Okay. For the next step, if we consider like the volume of the solution in the fixed bed at any time, that's right. If we consider at any time, previously we talked about the overall. If we balance at any time, that's right. It has more volume, high set and set data set. That's right. For this case, there are accumulation. There is no accumulation. If we consider in and out, that's right. Flow in, out, when not solute adsorbent. Right, when not solute adsorbent. Okay. Talk about the accumulation. For this case, we have no accumulation in the small volume cell. Flow in C at set minus C at set book data set. That's right. C at set minus C at set plus data set. That's right. The input is output. That's right. And also, this is concentration. Concentration is the mass or mole per volume. That's right. Mass or mole per volume. You have to multiply with volume. A is the cross-sectional area. U is the velocity. That's right. This is the volumetric flow rate. That's right. Volumetric flow rate multiplied by C, you get mass rate. Okay, this is mass rate. And also for this case, minus amount of solute adsorbed on the surface of the solid. Ka. Ka is the mass transfer coefficient multiplied by surface area divided by the volume. A data set is the volume of the cell. C minus C star. That is the rate of adsorption. Rate of adsorption. Okay. And then you apply the limitation. As a limitation, you divide this by A data set. In this and in this. For this case, A data set is cancelled. And it is C set plus minus C at set plus data set divided by data set. You take the limit, you get DC by DC. DC by DC. That's right. And minus U DC by DC minus KAC minus C star. You get it for the mass balance around the cell. Right. Okay, and then you rearrange and integration. That's how you take integration. You get like this set from 0 to the length L of the height. U over Ka is some constant. Okay, you integrate from feet to the C, dc divided by C minus C star. And this is equal to U over Ka integrate from C to Cf. That's why it is minus. If you replace this by Cf and this is C, okay, the minus sign is appear. Get this? And then you can calculate the height of the column L equal to U divided by K integrate from C to Cf dc divided by C minus C star. That's like you can estimate U or L. So you can estimate the length or the height of the column if you know the equilibrium relationship. You can solve it by integral if you know in the data or analytical data. If you know Q, you know C star. Like this, if you know the operating line, you know the equilibrium line. You can plot 1 over C minus C star. If you plot 1 over C minus C star and C, you get integrate from C to CF. This is the integration. It's the area under the curve, right? This is under the curve from CF to C. From C to CF. This is CF. Only CF is higher than C. You can integrate the area under the curve of 1 over C minus C star versus C. You know this curve, you can read from CF. It is CF. This is Q, Q star. And then you can read C and Q. C for this and Q for this. If you see this, calculate Q like this. You get C and Q, and then you can plot 1 over C minus C star. For this C, how about C star? This is C star. This CF, the C star for CF, it is something like this. You can read C and CF, C and C star, C and C star at any point from C to CF. And then you plot like this, you get the area under the curve, and then you substitute it, you can calculate the height of the column like this. Okay, I will talk to you about the example for the next lecture. I will stop the lecture now for this.